and whiteboard. Can all of you see the whiteboard?
Yes, sir.
Yeah. So let us now start doing a problem, and because I want to wrap this subject up, move on to enzyme kinetics. Your previous batch, I taught only enzyme kinetics. I mean, and I was not able to complete it. So obviously, the more time I spend on this subject, the lesser time I will have on enzyme kinetics, and then I will not really be able to do justice to that. And so I am under a certain amount of time pressure with such small semesters and a very large syllabus which doesn't allow me to go into depth. But let me sort of give you a flavor of the kind of depth that one needs and the kind of breadth that one needs in this kind of topics of recombinant protein production. I will give an example. I suddenly discovered this a question that I had given, I mean, almost 10 years ago to IIT Madras BTech students of biotechnology. And this was an exam question actually. It was a design problem that I had given, design a reactor, and it was on recombinant protein production. And after that, things did not turn out very well. Design a bioreactor because the head called me and told me, please don't give such questions. It is an open book exam. Those days, open book exams were a rarity. Nowadays, it's a common thing. 10 years ago, it was a offline class, and so it was a just. So design a bioreactor to produce recombinant protein, and I don't want to give you similar problems, though I'm told that in IIT Delhi, if students complained against difficult questions, no action is taken against the faculty. Unlike IIT Madras, where they shouted at me. Sorry, that was a joke. So to produce recombinant protein. Now, what was the question? Yeah, let me sort of give the question first, and really then we will talk about it. So design a. Now, the question was the following. Here's the question. So you have a clone. You have inserted a plasmid and in a bacteria, E. coli, let us say, you have E. coli, a recombinant E. coli, and a strain. You have a recombinant E. coli strain, which in shake flask produces 20% product, which is the protein of interest, 20% of the total cellular protein, the total cellular protein. How do you know that? My students would have shown it to you in the lab. You run a gel, and I'm sort of making the problem. And when you run the gel, you get bands of the cell lysate. You break the cells, and you get a bands of the cell lysate. And when you get the cell lysate, your desired protein is somewhere here. Of course, it doesn't come up in a different color. Sorry. Can you hear me, all of you?
Yes, sir.
Yes,
Yeah,
sir.
so this is the desired protein. This is just made red, but it's a thick fat band, and from the size, etc., you can make a guess that this is the desired product. And from various scans of all the products, and you know how much protein you have loaded, and there's some way to estimate this product, you find out that this is 20% of the, because you load the total cellular protein. So this is called TCP, total cellular. You have loaded the cell lysate, which contains all the proteins in an SDS page. And so you get the desired product as 20%. So you have a recombinant protein which is produced in shake flask, produces 20% product, and you know this. And for this, you need to grow it in log phase. And so essentially, that is biology stocking log phase, grow at a mu of, let us say, we talked about earlier, at mu of 0.3 hour inverse. Okay, and product reaches 20% and doesn't increase further, reaches 20%, that is the maximum value, that is the max value, in 2 hours, post-induction. And after that, as I talked about, CSR gets triggered, etc., and there is no growth, there is no further product formation. 2 hours, and then doesn't increase, and then stops increasing. and then stops increasing further. So you have to stops increasing further. So really what we are saying is that the fermentation, any fermentation that you will do, that has to be stopped. Fermentation, any fermentation strategy will be fed batch. The fermentation strategy will be fed batch and grow the cells. I mean, essentially grow the cells to high cell density, grow the cells, and then induce at a reasonably high OD, at a high OD. And these are, I'm writing this out. I mean, this is very obvious. I'm just sort of repeating what induce at a high OD, and after 2 hours harvest. After 2 hours harvest the cells. Because after 2 hours you are already got your maximum protein, which really is 20% of the total cellular protein. Got it? So this is what you have designed as a this is your biological statement. You have recombinant E. coli in shake flask, 20% product gets produced at within 2 hours, which is 20%, doesn't increase further. Preferably you need to grow it in log phase, which means you have to grow it at mu is equal to 0.3. Now, what is the engineering problem? The question. This is the background. These were all assumptions. You have to make certain assumptions. You are asked by industry to produce a ton of products, because this is a sort of industrial enzyme. You have to produce 1 ton of enzyme per year. Okay, and you are told here is a 1,000-liter reactor. Here is a 1,000-liter reactor. You have to produce. This was the question. 1 ton per year production of enzyme, given this background of the biologist. And you are told that here is a 1,000-liter reactor. And when you make the reactor, the question that the person who is designing the reactor is asking you is what should be the KLa? This was the problem. What should be the KLa? This is a typical design question that you should be able to answer, making various assumptions along the way and suppositions, and then designing how should you find out. This is a very simplified design problem. The real design problem would be obviously much more complex in actual industry, but this is the kind of problem that we face when we are told in industry to design a reactor for production of recombinant protein. So one of the first questions they will ask you, what is the size? Well, we decided that the size should be 1,000 liters. And the second question is, what should be the RPM? And the size of the impellers, and what should be the RPM? And remember, really the question on what should be the maximum RPM and what should be the design of mixing is really what the question really translates to, what should be the KLa? Because really the question is, can you hear me?
Yes, sir, yes.
Yeah. So really the question is that KLa is really a function of RPM. So when somebody asks you what is the RPM, what is the size of impellers, what is the number of impellers, Rushton stirrer, etc., 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 really what the person is asking you is what is the KLa? And your KLa is to be determined from this kind of design. Now, how do you answer this question? And this was the question I gave to IIT Madras students, BTech students in the exam. And of course, there were all kinds of complaints against me. So I will not give it again. Though I think, so because I think design is about connecting the dots and making the assumptions. And I think many students felt that this was very far away. That the connection between KLa and this is a bit far away. And it is this ability to connect the dots which is the most important ability of an engineer, to look at across fields. So this part, as you can see, the background is really the background for recombinant protein production, which is the enzyme technology that I'm talking about. This is molecular biology, and this is fermentation technology. And you're supposed to connect the dots between fermentation and. Now, how would you go about it? Let's have some answers. Have you understood the question? All of you? Hello?
Yes, sir.
Yeah, so now start solving the problem, start making it simple. Let us have answers, quick answers. अरे मैंने ये क्या किया? Oh God, सभी है, कोई बात नहीं, doesn't really matter. Okay, so let us start. Let us start with the simplest point. 1 ton per year. 1 ton per year. Okay, let us say 1 ton per year चाहिए हमको. Now let us go backwards. I mean, I'll do it very quickly. Let us say each batch of E. coli, each fed batch run, somehow you are able to finish it within 24 hours. These are very crude assumptions. 24 hours, 1 day batch. Each fed batch run 24 hours, 1 day, and cleaning and washing and rerunning and adding media and re-autoclaving the reactor is wrapped up within that same day by people who are working very efficiently. So really you can take 365 runs, or let us say, to be on the safe side, 300 runs per year. Obviously that is the first easy assumption. 300 runs per year, which means 1 day batch, 65 days of downtime, 300 days, 300 runs per year, because E. coli, the what do you call it? The runaround time, the time which requires you to restart the fermenter is within 24 hours. Let us say the fermenter ran for 18 hours or 20 hours, and within 4 hours you cleaned it, removed the material, sent it for processing, and the fermenter was ready the next day. So this is of course a very bad assumption. It never happens in actual practice. You can get only about 150 runs or 150 runs a year. But let us say I can take 300 runs per year because I'm super efficient. So 300 tons per year, and let us say that let us also make a second assumption. What is the recovery? Purification recovery. Let us say recovery percentage recovery in during purification. So let us say during purification, and you can see that so if 300 days runs, so if it produces X amount of protein per year per run, X kilograms, let us say. So let us say 300 into X. 300 into X is the amount of protein produced per year, that is equal to 1 ton. And let us say that the recovery is 2/3. Let us say recovery during purification is 66%. I'm just making some easy assumptions. All of these are wrong. So really that becomes 200 runs per year, equivalent, sorry, 200x actually. I should not say 200 runs. Actually it's 300 runs, and each of these is producing X. So 2/3 into 300x, 200x is equal to 1 ton. So therefore X is equal to 5 kilograms. 5 kilograms is what we need per run to be produced. Sorry, 5 kilograms is the final product per run after 66% purification recovery. And we have to find out these things. I mean, I'm just sort of jumping through these steps because really this is not the main problem. Each of these has to be actually separately calculated. So X is 5 kilograms, volume is 1000 liters. Sorry. So X is 5 grams per liter. Is this all right? I jumped through these steps?
Yes, sir.
Okay. Yeah. So now you want 5 grams per liter, and you also know that your biomass. So what if X is 5 grams per liter? Sorry, I should have called it P. P is 5 grams per liter. Then what should be your X, which is the biomass concentration? What should be the biomass concentration? Now, for that, this very simple question that you must have always handled reasonably enough. So you know that we are talking about biomass concentration in terms of dry cell weight. Now you know that cells compose of various things, but approximately, I will write it approximately again, about 50% total cellular protein. So if the dry cell mass is 1 gram, the total cellular protein is about 0.5 grams. Actually 0.52 or 0.55 is more correct, but for the safe side, we will take 0.5 grams. And out of this, 20% is my recombinant protein. So in a very simple sense, 20% is my recombinant protein. So what does this mean? My Yp by X is a constant final value. My Yp by X final is nothing but 0.2 into 0.5, which is 0.1 gram per gram. Are you following this argument?
Yes, sir.
Yes, sir.
Yeah. Okay. So therefore, my X final has to be 50 grams per liter. So this is what I can finally. So I very quickly reduce the 1 ton requirement to the real question, what should be my X final? Now you see, the connections are now being made with mu. And now it is a very simple step. If X final is 50 grams per liter, right, and let us say that it is made in 2, and remember that the induction is at 2 hours, and I will introduce one minor point. Induction is 2 hours before. Now the cell is growing at a mu value of 0.3 hours. The cell has to grow at 0.3 hour inverse, and 2 hours before, if the final biomass is X final is 50 grams, and now I will make this assumption, which is not correct. This is a hugely incorrect assumption, but for calculation purpose, otherwise it will become it will not become tedious. You'll have to do the calculation actually. X final is 50 grams per liter. Now what is the mu value? And that is the real question. What is the mu value between the point of induction and after 2 hours? And that mu value is obviously falling, right? It's a complicated question because mu is 0.3 at point of induction at 2 hours before. So your cells are growing like this, exponentially, right? And somewhere this is X, this is T. Are you following me? And at some point here,
yes, sir,
I am inducing. And then the moment I induce, my growth rate will fall. And this is 2 hours. This is 2 hours. And 2 hours later, this point here is 50 grams per liter. Are you getting this point? All
yes,
of you?
sir. Can you please explain like why the growth rate is falling after induction?
अरे आप भूल गए भाई, previous class में मैंने क्या पढ़ाया था? You did not listen to the last class. Post induction, a cellular stress response is triggered. फिर से उड़ गया. A post induction, a CSR is triggered, a cellular stress response is triggered, which downregulates growth, downregulates protein formation synthesis, and ultimately stops everything. That is why after 2 hours there is no further production.
Yes, sir, yes.
And no further. So now I will not do the mathematical details of CSR into this problem. It can be incorporated. Let us make the very crude assumption. Let us make a very crude assumption. I mean, that's a very slightly wrong assumption. But चलिए कुछ तो करना पड़ेगा ना problem solve करने के लिए. अभी फिलहाल हम लोग we cannot get into the very fine details of the problem. Let us make the very crude assumption that the growth rate is approximated by this kind of thing. Some growth rate is approximated by this point. And let me say, so this is, I hope you're familiar with this kind of line. This is what is called linear growth, which means it is increasing linearly. I hope you all realize that linear growth is a very good approximation of declining exponential growth. And that is what we are claiming, that because of the cellular stress response, there will be decline in the exponential function. But ये ऐसे गिरेगा, a dotted line, but I have sort of approximated by a straight line. Are all of you with me following this argument?
Yes,
Yes, sir.
No.
Yes.
So I am saying that this, instead of declining exponential, I approximate my model to a linear growth model at this point of time for 2 hours. Right. Now it's a very simple question. Now it's a very simple point, and I will do this very little bit of arithmetic to sort of solve this problem. Okay, I should not rub this out. Yeah, but it's all right, you remember this. Your X final is 50 grams because that is what is required to get, 5 grams per liter because your YP by X is 0.1. Now, if your X final is 50 grams and you are getting linear growth and your mu at the point of induction was 0.3, can you now do some simple arithmetic? Now, this is 0.3. What the hell? If mu is equal to 0.3, now what should be X at induction? What am I saying? I hope you understand what I'm saying. X at induction.
Yes,
So
sir, yes.
here is X at induction. At this point, X at induction, it will be growing at mu into X, which is equal to 0.3 into X is equal to D. 0.3X is your dx by dt. So, okay, because dx by dt is equal to mu into X. At the point of induction, it is growing at 0.3. So your dx by dt at induction, at the time point of induction, is, why is it not writing? At the time point of induction is 0.3 into whatever is the X. Maybe 30 grams, maybe 20 grams. And in the next 2 hours, this 0.3x is now fixed because I am saying it is linear growth. So dx by dt is now a constant. It is now constant linear growth, and dx by dt is a constant. Notice it is not mu into x which is constant. It is dx by dt which is constant, which means mu into x is a constant, which means as x increases, mu declines. In exponential growth, mu is a constant. So dx by dt is, as you all know, exponential function derivative is also exponential integration, is mu into x, which is equal to x naught e raised to mu t. So notice that dx by dt is always increasing because mu into x naught is constant into e raised to mu t. So dx by dt also increases exponentially. But for linear growth, your dx by dt is a constant, and therefore mu into x is a constant. Therefore, by definition, mu declines as x increases. That is the basic assumption we have made for our CSR. It's a crude assumption, but nonetheless reasonably valid. And so, at the point of induction, my growth will become linear. Okay, and therefore it will be growing at the point it was growing at the point, and at the time point of induction, if x is the concentration here, if x is the concentration here, then the rate of growth is mu into x, which is 0.3 into x, which is equal to dx by dt. And this into 2 hours, is the amount of increase in biomass. Notice that this slope here. So now this is 2 hours. This is, and the slope is 0.3x. This point is 50. What is this point? What is x equal to? Come on.
31.25.
31.25. All of you are getting this? Hello?
Yes, sir.
Okay. So you can see that dx by dt. So the assumption of linear growth or declining exponential growth has now allowed me to determine the point of induction. At this point of induction, my x is equal to 31.25 grams per liter, which means that my mu into x, if mu is constant, till this point I have continuously increasing oxygen demand. Now, and this is a very interesting point that I want to make, and the whole purpose of why I chose declining exponential to be approximated by the linear growth model. So you can see that x is increasing, and X at the point of induction is 31.25 grams per liter. And so the rate of growth dx by dt has been also increasing, which is given by 0.3 into X, which is at the maximum 31.25. Now this is dx by dt max also, which is equal to how much? Approximately 10. And let us not get 9 point something something. 10, approximately 10 grams per liter is the maximum per hour. The dx by dt max is given by 10 grams per liter per hour max. Notice that this dx by dt max is now held at dx by dt max. Do you realize the interesting implication of this? It means that till the fed batch was running, my feed was also increasing exponentially. Right? Because my biomass was increasing and my feed had to increase because dx by dt was increasing. At this point, what will happen to the feed? This is F. And this is X. This was X. So, can you tell me, any of you tell me, this was X, this is F, the feed. So, at the point of induction, how should the feed go after induction? Post-induction feed kaisa hoga? The question that I'm asking all of you is, what should be the post-induction pattern of the feed? Post-induction. Bataiye, hello? Loudly, please.
The substrate would so it would increasing. Means
Kaisa increase karega?
like
So
more
I'm
faster.
asking you the question, what is the post-induction feed profile? See, earlier, pre-induction feed profile, pre-induction feeding profile is exponential, right?
Sir, one thing,
Agreeing to this?
I have one doubt.
Yeah.
Sir, after induction, the linear growth is happening. What is the slope
Yes.
of that line?
It is equal to the slope of, actually it's बहुत खराब drawing, this is a bad drawing, but it is equal to this slope. ये actually ऐसे जाना चाहिए था, मैंने drawing के लिए ठीक सिर्फ explain करने के लिए किया. It is equal to the dx by dt at the point. See, I chose this value and I said this linear growth is exactly equal to, okay, so I will, जगह नहीं है, बट ये क्वेश्चन आप याद रखिए, आपको हमें पोस्ट इंडक्शन फीड प्रोफाइल बताना है, म्यू 0.3 है. सो एक्चुअली लेट मी wrap this out. So no, I mean, it is a good thing you asked because some of you might get confused. So really, the drawing, I should make a good proper drawing so that you understand what is happening, because a figure is always a better idea. So look at this. See, pre-induction, this is increasing. Are you getting the point? This is an exponential function.
Yes, sir. Yes.
It is, the slope is increasing. At this point of induction, this thing becomes constant. Notice that if it were exponential, it would have gone like this. The slope would have kept on increasing. At this point, the slope becomes a constant. So this is linear, this is exponential. This dx by dt, this is x, this is t, is equal to, this is equal to the dx by dt here. These are equal. But now this dx by dt was equal to mu into x till this point, and it was increasing continuously. Increasing continuously. At this point, this is the linear phase of growth, and dx by dt linear growth, and therefore dx by dt is now equal to a constant. Biomass is increasingly dx by dt is not zero. Okay, dx by dt is not zero. It is a constant. It's not zero. It's a constant. So this line will go like this. And this point here, 2 hours later, trouble करने लगा है. Can all of you hear me? This point here,
Yes,
2
sir.
hours later, is 50 grams. This point here is 50 grams. And therefore, as you guys calculated, this point here is 31.25 grams. And therefore,
Sir, how
this
can
point
we
here,
calculate 31.25 grams?
and therefore dx by dt is equal to 31.25 into 0.3, which is 9.375,
Sir,
which I approximated as 10. Yeah.
we cannot calculate. How can we calculate, like, at the point of induction, the amount of biomass X is equal to 31.25 gram? We don't know the time interval, the time at which the induction we are doing.
We don't know the time of induction. This time we don't know. ये मैं कर सकता हूँ calculate, वो उसके पीछे assumptions करना होगा. This time is unknown. But we know that this is 2 hours before. This time we don't know. But this gap is 2 hours, that we know. And we know that the final biomass is 50 grams. So we know
Yes,
that this biomass is 31.5. ये टाइम हमें नहीं पता है, ये एक्सपोनेंशियल ग्रोथ का टाइम हमें नहीं पता, वो कैलकुलेट कर लेंगे हम लोग, वो बहुत मुश्किल काम नहीं है. दैट्स अ सिंपल इजी टास्क फॉर अ स्टैंडर्ड बायोरिएक्टर डिजाइन कोर्स. दैट इज व्हाई आई एम नॉट टचिंग ऑन दिस. I am touching on post induction, which is the focus of bioreactor for recombinant protein production. This part you all know how to calculate. 31.25, 0.3 mu है, कुछ lag phase calculate करिए, कुछ initial biomass calculate करिए और कर लीजिए. ये सब मुझसे मत करवाइए. ये simple काम है.
sir, I did not understood, like, how did we go 31.25 gram, or whoever was saying that, I don't know.
Because we calculated backwards. You have not been listening. You see, this point is 50 grams. Did you follow this argument? Why should it be 50 grams?
Yes, sir. Yes.
So, and this 50 grams has to reach within 2 hours. Because 2 घंटे के बाद production नहीं होता है. Did you agree to this
Yes,
point?
sir. Yes,
So
sir.
therefore, the question is, if this is 50 grams, 2 hours earlier, I did the induction. And 2 hours earlier, when I did the induction, I had some concentration X of the biomass. Okay?
Yes, sir.
कुछ X होगा ना, पता नहीं मुझे कितना है, ये आपको निकालना है. And this X at that point of time was growing at 0.3x. Because obviously I want to maintain mu at 0.3. Is this argument clear? Mu is equal to
Yes, sir,
0.3x. So now, and after, at this point, when I induced, the moment I induced, my growth stopped, my growth became linear instead of exponential. So earlier my dx by dt was 0.3x. Space बहुत कम है. I need a big blackboard to teach this kind of stuff. 0.3x e raised to the power of mu t, right? Now it gets frozen at 0.3x. This increase no longer takes place. This increase does not take place any further. It becomes linear because of CSR. As an approximation of the CSR response, I say that my dx by dt becomes 0.3x. Actually, it becomes a complicated function. It gets like this. But let us not get into that. Let us say that as a simple approximation, first level approximation, it becomes equal to 0.3x at x at the point of induction. And this 0.3x, and this is x, and the slope is 0.3x, and it is a constant. After 2 hours, it becomes 50 grams. Are you all right? Are you following? All of you?
Yes, sir. But in that case, there is no, when we are considering
अब आप
e to the
इस
power
प्रॉब्लम को सॉल्व
mu
करिए.
is equal to 1. Yes, sir.
करिए ना बैठ के कैलकुलेट. मैं क्यों, मुझसे क्यों पूछ रहे हैं? मुझे बताइए x क्या है? I think one person calculated it and all of you nodded your heads. That is the bad strategy. All of you take 2 minutes and find out x. If x is here, 50 is here, this is 2 hours, and the slope is 0.3x. Okay? The slope here is 0.3x because that is dx by dt. It is this part only. Can you see the board? dx by dt is
Yes, sir, we
0.3x
can
because
see.
it's no longer in. तो ये 0.3x है. So ये slope जो है, ये slope जो है, अब आप ये सब में dx by dt constant है, ये सब लिखा हुआ है मैंने. So this slope here, this slope here is 0.3x. This time here is 2 hours. This point here is 50 grams per liter. What is this x? अरे एक मिनट में. So what is this point? X is equal to what? Go back and calculate. Don't rely on one person. How will you calculate? Please tell me. Who was it who calculated it? I didn't get. I mean, I can't see your. I could just hear you. Sorry?
I calculated it, sir.
Yeah, so please tell me how you did it. Please,
So
please run us through.
50 minus x at the point of induction divided by 2
50 minus x divided by 2 is equal to?
equal to 0.3 into x.
That's simple enough. So we
Yeah.
get, how do we, so at 50 minus x, अब भाई साहब आप लोग हमें रिड्यूस करेंगे क्लास 11th का पढ़ाने का काम, मुझे बड़ा अच्छा लगता है, but
Sir, in this case, I got it, but the thing is that dx by, when we are assuming that dx by dt is equal to 0.3 into x induction, we are aren't we assuming that we, even before the point of induction, there was growth was happening linearly and not exponentially.
अरे ये ड्राइंग देखिए केयरफुली भाई रत्नेश जी, मतलब यू नो डू नॉट आर्ग्यू इन अ वेरी मीनिंगलेस वे टिल द पॉइंट ऑफ इंडक्शन. भाई ये तो बड़ा मुश्किल है. आप बहस, मतलब बहस अच्छा लगता है मुझे, लेकिन ये बहस के पीछे तर्क होना चाहिए. आई विल राइट इट. टिल द पॉइंट ऑफ इंडक्शन, which means pre-induction. The point of induction is a single point, which means pre-induction. The computer also is now very behaving. Sorry for all this. Till the point of induction, which means pre-induction, mu is equal to 0.3. This way, I mean, at some point I have to stop this debate because otherwise we will not be able to progress further. Pre-induction, mu is equal to 0.3 and a constant, which means all the way from here to here, it is exponential growth. What is wrong with this statement? At the point of induction, exponential growth ceases and becomes linear growth. What is so difficult to understand about this?
Okay, sir, understood.
So till the point of induction, it is mu is equal to 0.3 and x is increasing exponentially, mu is a constant. At this point of x, I add inducer and immediately it becomes linear. Obviously, it does not become linear immediately. It continues exponentially, but it declines. It's a complex phenomena. I have made a crude assumption that post-induction, dx by dt is a constant and not increasing anymore. So I have therefore, what it has done is to allow me to calculate dx by dt max. And the dx by dt max is 0.3 into 31.25, which is nothing but 9 point something, whatever, which is approximately 10. 9 point something, which is approximately 10. So the whole purpose of this exercise was rather simple. That my dx by dt max, which is increasing till the point of induction and is maximum, is this is at the point of induction. Because dx by dt has been increasing till the point of induction. And after that, it doesn't increase further. So is equal to 9 is approximately 10 gram per liter per hour. Bad drawing. So my question to you guys was very simple, that if this is the growth profile, notice increasing, point of induction, and then becoming linear. Same slope. Rather than going like this. Okay, so this is how the biomass is going. My question to you was, if this is the feed, this is also increasing exponentially. Sorry, bad drawing. This is F. What should be the F post induction? How should it go? How should F? इसके बाद कैसा होगा? Hello? Hello?
Yes, sir.
What should
Yes,
be
sir.
F
Yes,
post
sir. We
induction?
can.
Tell me, this is one. What is the post induction feeding profile? The pre-induction feeding profile is exponential. The pre-induction feeding profile is exponential. हाँ बताइए भाई.
Sir, should it be linear?
Linear means what? Like this?
Yes, sir.
सोचिए. What is feed? What is feed proportional to? Feed is what? Feed is ds by dt, right?
Yes, sir.
Amount of supply, है ना? Right? Rate of increase. And ds by dt is proportional to what? dx by dt. If ix by s is a constant. So if feed is ds by dt, it represents increase in substrate concentration, and that is proportional to dx by dt. And dx by dt is now a constant. भाई आप लोग ये linear नहीं होगा. This is wrong. It should be like this.
Constant.
It should become a constant, because this constant feed, the feed, remember that the feed represents the derivative of the biomass. This is x. The derivative dx by dt of this line, and this is an important point, but interesting that you forget. There is a dx by dt associated with this line. So if you take the derivative of this line, dx by dt, you will get it proportional to the feed. Are all of you following this very interesting concept?
Yes, sir.
Yes, sir.
So it is a derivative of this line which is equal to this. So when this line, black line, becomes post-induction a constant rather than increasing, the derivative of this constant is a straight line like this. It's a constant, not increasing. The derivative of this is not this. The derivative of this is not this. The derivative of this is this. Correct? So feed becomes constant. And do you realize why I made this statement about feed? Feed is increasing. Similarly, oxygen is being fed. Oxygen is introduced continuously. See, feed, oxygen, they are being introduced continuously, and therefore they represent the derivative of the biomass. And so, in a very interesting way, the oxygen requirement also mirrors the feed requirement. Do you realize this argument? The OTR, oxygen transfer rate, which is equal to the oxygen uptake rate, which is OTR is KLA C star minus C, which is where we'll come back to the argument. But OUR, the oxygen uptake rate, what is it proportional to? Mu into X upon Y X by O. And mu into X is nothing but dx by dt. So the oxygen uptake rate is not proportional to the amount of biomass, it is proportional to dx by dt. So obviously, and that's obvious common sense if you think about it, obviously it is the oxygen requirement or the feed requirements are the oxygen uptake rates are not proportional to mu or x. It is proportional to mu into x because it is equal to dx by dt. So the oxygen uptake rates are proportional to dx by dt, just like feed rates are proportional to dx by dt. Please remember, it is not proportional to mu, it is not proportional to x, it is proportional to mu into x. Because it is the rate of increase of biomass which determines the amount of oxygen uptake. It is not biomass which determines, it is not mu which determines. It is the multiplication of the two. जितना तेजी से biomass increase करेगा, उतना आपका oxygen uptake rate बढ़ेगा. And so your oxygen uptake profile will be increasing till the point of induction and then becoming constant. Yes, please. Hello. Any questions? And therefore, this is a very important conceptual point. Therefore, your OTR increases like this and then becomes a constant at the point of induction. So notice that the maximum OTR is at the point of induction, after which it remains at its maximum value. Are all of you okay with this point? Because oxygen transfer rate is equal to
Yes,
oxygen
sir.
uptake rate if your C star value has to be a constant. C is to be a constant. Because remember that oxygen transfer rate, आपने एक क्लास के प्रॉब्लम सॉल्व करने में पूरा क्लास अगर खत्म कर देंगे तो बड़ा मुश्किल होगा भाई, ये बहुत स्लो पढ़ा रहा हूं मैं. I have to increase the speed, but I cannot increase it if you don't follow. So I hope you follow, and that is why you realize that IIT Madras students, why were they so angry? So because they had to introduce all these concepts. So OTR is KLA, C star minus C, and this C is minimum, C minimum, some that your E. coli, that your recombinant strain, recombinant E. coli strain can tolerate, because you have to design, these are all, as I said, part of more complicated. So it can tolerate this. So let us say it can tolerate C minimum of 20%, and C star obviously is 100%, and your, so that into KLA. So KLA 100% minus 20%. I hope you know that C star is approximately for media 8 milligrams per liter or something like that. I don't remember. And so you can find out KLA into C star minus C, which is 100 minus 20. That's 80% of 8 milligrams into KLA is equal to your OTR, and your OTR is equal to OUR, and your OUR is nothing but dx by dt divided by yx by O. And from stoichiometry, and now I'm moving very fast, I hope you know how to calculate yx by O from stoichiometry. You have done a course on mass and energy balance. How to calculate yx by O? What is the oxygen required per gram of biomass produced? What is the grams of oxygen required? Or what sometimes we do it as mole per mole. What is, or sometimes we use C mole concept. I do not know. Are you familiar with C mole concept? C mole by C mole? Where you write E. coli or any other organism in terms of C, C1. So instead of glucose being written as C6H12O6, the C mole style of writing would be C1 and H2O. So you make it C1. So ethanol, instead of writing C2H5OH as a product, you will write it as CH3O.5. So this is called the C mole concept. We use C moles so that we can always use one carbon. Helps in material balance, which you would have done earlier. And so therefore, biomass is often written as, what is it written as? All of you, can you remember? Is often written as CH 1.8 or 1.79, depends on you, 0.5 or 0.48 or whatever you want to, and N.2 or 1.8, doesn't really matter, something like this. So, other things are very small. P and S are all very small. So we rate it as C1. So this is biomass, and this is 1 C mole of biomass. This many grams, if you calculate it, is 1 C mole. So you can calculate Yx by O in terms of C moles per mole of oxygen, C mole per mole, which is an easy stoichiometric calculation which you must have done in your earlier courses. So if you know your Yx by O, then Yx by O, if you know it, then you know C star, C minus, you know what is C star, you know KLA, you know Yx by O, so you can calculate the KLA. I'm not going to do all the bioprocess calculation. This is something which you have already done. So your KLA can be calculated. So you can tell people, this is the KLA I want because I want to make proteins of 1 ton per year. So you realize the connection between molecular biology and fermentation. Is the problem clear? I of course ended it very quickly because I'm running out of time and I want you people to ask questions, and I want to wrap up this subject and go on to enzyme kinetics. But do you follow the connection between the bioprocess design, the molecular biology design, and the desire for producing recombinant protein? Did you follow this?
Yes, sir. Yes.
All of you, questions? Not one person. Any questions? So I hope you know how Yx by O and all are calculated. This is something that I don't want to teach. I don't want to get into stoichiometry of biological processes. This is a course which you must have done earlier. So KLA can be calculated based on the oxygen requirement, and the oxygen requirement can be calculated based on not just Yx by O, but your understanding of the mu into X at the point of induction. So this is the way we design reactors for enzyme production. And this is the connection between the two. And I thought this is an important subject to sort of highlight. From now onwards, we move back to molecular biology. From tomorrow, we will keep jumping subjects. That's important. We'll move back to molecular biology where we will talk about location of the protein. We talked of total cellular protein, and this is 20% of total cellular protein. But how do we design location and how does it help or hinder? And so that will be the last class, I think, on protein production. There are other aspects of protein production, fungal protein production, so on and so forth. I think, I'm sorry, I mean, I can't teach it. I find it very boring. I don't want to. Industrial microbiology is not something which I like teaching to students. It's an important subject, but let us give it a pass. Unless, of course, you want to learn it, because I want to move to enzyme kinetics now. We are running out of time. Any questions, or shall we stop here? I mean, I want some feedback. If not questions, feedback. Is the way that I'm presenting the problem understandable? That is the first requirement. Be interesting, or something which you have not done before, or something which is actually being repeated, which you have done before. Some kind of feedback would be helpful. Because the same questions I will ask even while doing enzyme kinetics, because I do not know at what level you understand kinetics. All of you must have heard of Michaelis-Menten kinetics. So if I repeat that, it's simple. But if I start talking about feedback, allosteric mechanisms, then the maths becomes extremely irritating and tedious. So that also I don't want to do. So I want to pitch my lecture at a level which you people have not done before, but not so difficult that you'll find it hard to follow. So that is the question that I'm asking here. Is it something which you have done before, or you find it too hard to follow, or is it just the right amount? Some feedback would be appreciated.
We have done it in separate parts, as in calculated the KLA for different conditions are given, and then we calculated. But
Okay.
all the things at once, we did it today itself. That is in this class.
Yeah, so that is the whole point. Yeah, you would have done KLA calculations, but KLA calculations in terms of dynamic gassing out and stuff like that, you're saying?
Yes, sir.
Yeah, but that is a different point altogether. That is how to calculate KLA once it is given to you. Here, what is the design KLA? This is a slightly different question, isn't it? What is the design KLA that you are demanding from the fermentation design fellow so that you achieve a certain OTR, so that you achieve a certain OUR or an OTR, which then allows you to achieve a recombinant protein production of 5 grams per liter. That connection was important, because now I was sort of insisting, I was making this argument that you are forced to have a mu optimum equal to 0.3 till the point of induction. So you're forced to grow the cells exponentially till the point of induction. and the point of induction is determined by your final biomass and product yield, and therefore you have to grow it exponentially, and therefore you have a certain KLA requirement. So that was the connection I was trying to do, and I hope you have done this. So I do not know whether you have done this kind of demands before, that I demand that this is the KLA, and that KLA demand really is determined by the demand for a certain mu and the demand for a certain X. The demand for a certain mu cannot falling below 0.3 is from the issue of recombinant protein production, because as I pointed out, and these are things that I didn't want to talk about in the class, but because as I pointed out that really the issue that has been taught to you by recombinant protein is that QP versus mu is a plot like this, and so I need mu optimum equal to 0.3. So therefore I have to ensure that till the point of induction mu has to be equal to mu optimum, otherwise I will not get that high QP, and I didn't talk about that. I didn't talk about the kinetics of, and given this QP max, only then within 2 hours, in 2 hours, given this QP max, in 2 hours, the recombinant protein will become 20% or 10% of total cellular protein. So this process of making 20% cellular protein, recombinant protein as 20% is achieved only when QP is equal to QP max, which is achieved when mu is an optimum, because QP, let me say it's a line like this, maybe let us say proportional to mu, in which case it's a straight line, which is growth associated product formation. So these are the things that were in the background. I didn't want to talk about rates of product formation and put additional complexity. How does it make in 2 hours 20%? What is the QP requirement? How does QP fall post induction? How does the CSR impact on QP? These are all more complex questions. We will not address them. Okay. So any more questions? Shall we stop?
Yes, sir, we can. Like, we will have to do like Michaelis mental equation. We know the equation, but we have not done it before.
अच्छा ठीक है, ओके, हम आराम से शुरू करेंगे, don't worry. So shall I log out? So shall we stop recording?
Yes, sir. Thank you, sir.
Oh, thank you.
Thank you, sir.